Good morning, guys. Today we are doing power. So I'm going to try my best to walk us through this with the pen. The first thing that you have to take into account is that there is a voltage drop of an LED that is different than resistors. Resistors, their hunger depends on how big they are. LEDs have a fixed appetite. So our food supply, the LED is going to get 2.1 volts in this circuit no matter what. Whether there's a resistor here or not, the LED is going to get 2.1 volts. We have a resistor here to limit the amount of current that goes through this LED. So we have 9 volts is our circuit power or voltage. Let me use the word voltage because power is different. We like to call it turn on the power, but voltage is what is coming out of the battery. The resistor that we have, we're going to take that into account in just a minute because we need to find the total circuit current first. So we're going to draw a letter I. Current equals voltage divided by resistance. And this is also, for this example, written right here. This is your voltage. You have to subtract the LED voltage because it's already going to eat some of this food supply. So when you subtract 9 volts or 2.1 volts from 9 volts, you're left with 6.9 volts. And that is what's left of the power supply that is flowing through the resistor. So 6.9 volts divided by 470 ohms is the resistance in this particular series circuit. So 470 ohms is going to give you 0.0147 amps because we divided a unit by a unit. Volts divided by ohms, those are units. We didn't do kilovolts, we didn't do millivolts, we did volts. So that gives you amps. Then you convert by multiplying this times 1,000 will give you 14.7. And the milli tells us that it is 1,000th of an amp because we divided, we multiplied by 1,000. You have to divide by 1,000 to get back to your amps. Milli is telling you because it's 10 to the negative 3 or 1 over 1,000, you're dividing this by 1,000. It's the same number, but this modifies the number. And we've talked about this and talked about this. Hopefully, at this point, it makes sense. So now you have the total circuit current. Now, this says PIE. You can also look at the E as PIV. Pi is the old way of looking at it. PIV is the modern way to look at it. E stands for electromotive force. That's voltage. It's the same thing. So now that we have a current and we have the voltage flowing across each of these devices, because guess what? 6.9 volts, you've already figured out what the voltage is flowing through this when you did your subtraction earlier. All this does is prove to you that 14.7 milliamps times 470 ohms is still 6.9 volts. If you look at it like this, basically you're taking your answer that came from here and you're crossing out the ohms when you multiply times 470 and you're getting 6.9. That's all you're doing with this. So that might be a little confusing because I can't draw it very well on here. Moving along, now we're going to find the power. And these show you how to find the power. We're going to do current, which is 14.7 milliamps or 0.0147. I have to talk as fast as this thing will let me draw. That is how many amps are flowing. And we're going to multiply that times 6.9. So times 6.9 is going to give you 101.4 milliwatts, which is on your calculator is going to come out to 0.1014 watts. That is for the resistor. The LED has a fixed voltage of 2.1 volts. So you're going to multiply 0.0147 times 2.1 volts. Those are all units. You have watts, you have current, which is amps. Volts is going to give you 0.0309 watts, or 30.9 milliwatts. And that is the power that is going through the LED. Now, the other questions in this ask you, because at the beginning of this worksheet, I explained to you that, trying to figure out how to clear this. Do you hit the escape key? Yes, there we go. So at the beginning, we talked about a data sheet for an LED. Has a continuous forward current of 20 milliamps. That is the maximum rating to get the full life out of it. It has a power dissipation of 170 milliwatts. Now, there's more to that than we would explain in high school. In college, you would find out what the ambient temperature is, and there's a derated, you take away a certain amount of power that it can dissipate, because if you were to turn this thing on in an oven at 20 milliamps, it's probably going to overheat and die. And the maximum forward voltage, this is a typical electrical characteristic, is somewhere between 1.8 and 2.1 volts. For our circuit design, we're just going to go with 2.1 volts for these LEDs. On your test, it's 2.5 volts. The resistor has a power rating as well. That's a quarter watt, 0.25 watts. And a quarter watt is not a lot. Now, on this one, if you asked, is the resistor within its power rating? Well, 0.1014 watts is about half, give or take, it's half of a quarter watt, 0.250. And down here, 30 milliwatts, that's within the power rating of a typical LED, which has 170 milliwatts. That's within the rating. And the milliamps, or the forward current of it, because we figured out it's only 14.7 milliamps, it is within the power rating, or the current rating of the LED. So let's go work through this one right here together. Let me get the pencil back. We will suffer through the pencil. The first thing you need to find is the total circuit voltage is 24 volts. All I'm asking you for is to go ahead and write down your voltage so you can go ahead and find it. Now, the next thing that you're going to have to do is find the total circuit current. In this particular circuit, there's only one resistor. It has a value of this food that you're going to eat out of the food trough. The LED is going to eat 2.1 volts out of this. So to find the total circuit current, you're going to go 24 minus 2.1. And this is what's going to eat up all the video time of this recording, is me writing this out. 2.1. And what does that give you? 24 minus 2 is 22. So this is 21.9 21.9 volts. Let me just go ahead and write that down. 21.9. Now you have your voltage that you found. That is also the voltage across this resistor, is 21.9 volts. That's how much it's going to see. Then to find the current, you divide by resistance. So that is dividing by 1200 This is what happens when you use free apps at home to figure things out. So we divide 21.9 divided by 1200 is going to give us 0.01825. So our current is 0.01825 amps. Now, we're going to convert that to milliamps by multiplying by 1,000. We get 18.25 milliamps. We already figured out that the voltage across the resistor is 21.9 volts, because this right here is 2.1 volts already. You subtract it from here. The next thing, the voltage across the LED is already given to you by the schematic, is 2.1 volts. Now all we have to do is find the power rating. And the power, remember, power is, there we go. The power is P equals current. I'm just going to draw a line for current. That's the I, times voltage. So you already have these values. You figured them out. The current is 18 milliamps. So on our calculator, I'm just going to use the calculator at this point because I think it'll be faster, because I only have 3 minutes left for this video. So to find the calculator, you click on the calculator. We have the current, which is 0.01825. You're going to multiply that times the resistance voltage, the resistor voltage, which is 21.9 volts. We get 399.6 milliamps. Let's just round that up, or watts. I'm sorry, watts. So round it up to 0.4 watts. Because this, if you go 3 or 4 places, all these numbers are greater than 5. That is 400, because you multiply times 1,000, 400 milliwatts. Now, let's go 0.1825. That is not correct. 0.01825 times, and 2.1 volts. That gives us 38.3 milliwatts, or 0.038 watts. So this, multiply that times 1,000, you get 38 milliwatts. Let me check my math because something doesn't seem right over here. 0.01825 times 21.9, I'm just checking my work, is 400 milliwatts. So the last question, is the resistor within that quarter watt rating? The power through resistor 1 is 0.4. 0.4 is greater than 0.25, so the answer is no. Is the LED within the 20 milliamp? Absolutely. It's 18.25, which is less than 20. So the answer is yes. It is within its rating. It will last forever. And it's 38 milliwatts. That is less than 170 milliwatts. So yes. So in this design, you would need to go back and maybe pick a half-watt resistor for this. Because really, if you're doing electrical for a vehicle, you can't change the battery. If it's a 24-volt diesel vehicle, you cannot change the battery. So if you need an LED to show that the battery still works, you're going to have to go with a half-watt resistor right here, because you can't change this. Or you could use more LEDs, or you could use an LED with a higher voltage drop. That is one other solution, but that might change the cost. A half-watt resistor is going to be a little bit cheaper. So that is how you're going to do all of these on this worksheet. This is exactly the same with a different voltage. This one is a different voltage, different resistor, same LED. This one just has 3 LEDs. So instead of 12 volts, you're going to see 5.9 volts because there's 6.3 volts coming from this. Alrighty, guys. Have fun working on this. I'm out of time. Have a great day. I'll be back tomorrow.